Hey everybody, welcome to another video. This one on simplifying radicals. Two types of problems that we're going to cover here today. Ones that involve objects that are more like this one here on the left, and ones that involve objects that are more like this one on the right. So, one thing you might be wondering is why do we even care about square roots? Well, square roots will appear when we have answers. We're looking for answers to problems that involve triangles. Who uses triangles? Well, a few jobs that use triangles are listed below. You've got carpenters, engineers, architects, construction workers, anybody who measures and marks land for development and things, artists, and in general designers. Those are some occupations that use triangles. Now, why are you going to need to know this? Well, even if you don't decide to go into any of those fields, this is a skill that you're going to need for your future math courses, things that you're going to use for later. So here we go. First part's going to be review. Second part, I don't know if you've seen before, and if you have, never hurts to review it anyway. So, two rules when we have simplifying radicals. First one is, when we're done, the number underneath the root should not be divisible by a perfect square, and there should be no radicals in our denominator. The bottom of the fraction should just be a plain old regular number. So let's say that we're asked to simplify something like the square root of 27. There are really two good methods that we have to do this. One of them is by using a factor tree. So if we start with the square root of 27, and we start breaking up 27 into parts, two numbers that multiply to make 27 would be 9 and 3. The 3 is a prime number, so we're going to circle it. 9 is not prime yet. We can divide 9 into 3 and 3. But 3 is prime, and 3 is prime. Now, anytime that you see a pair of the same number, what you're going to do is combine them. And anytime you have that happening, that means that you're going to have one copy of that pair move to the outside of the root, outside of the radical. So those two 3's are going to combine to make one 3 outside of the radical. Anything left over that doesn't have a pair, like this 3 right here, is going to stay underneath the radical. So we get 3 root 3. The other method is good if you know your perfect squares really well. Things like 1, 4, 9, 16, 25. Numbers that you get by taking a number and multiplying it by itself. If you know those really well, and you're pretty good with your number facts, then you might recognize that 27 is immediately the same thing as 9 times 3, 9 being a perfect square. That's why we use 9. If you recognize that, what you can do then is you can say that the square root of 27 is the same thing as the square root of 9 times the square root of 3. Now the square root of 3 isn't anything special, but the square root of 9, what number times itself equals 9? Well, that's 3. So then we can end up rewriting this as 3 times the square root of 3. So you can see that the answer in both of them ends up being the same thing. It's just that the method that we used to get there changed a little bit. We can apply similar ideas to this one. So let's say that you don't see any perfect squares fitting out of this number. What you could do then is start with method 1. 162. Well, I see that there's a 2 in this, and I know that 2 is going to be, that number is going to be divisible by 2 because it's even. So I can split this into 2, and 162 divided by 2 is 81. 2 is prime, so we're going to circle it. 81 is 9 times 9. Neither of those are prime yet, but these 9's are going to split into 3's, which are prime. So, remember, then you look for numbers that are in pairs. There's a pair of 3's, there's a pair of 3's. So we have two 3's on the outside now. They're going to multiply with each other. And that leaves us with this 2 that's prime by itself left underneath. So this is going to end up being 9 root 2. And as you can see from this method 1, the biggest perfect square that we can take out of 162 is 81. So for method 2, what we would end up doing is we would have square root of 162 turned into square root of 81 times square root of 2, which would then become square root of 2. So you get the same answer either way. Method 1 is really good if you don't know your perfect squares well. Works every time if you do it correctly. Method 2 is good if you do know your perfect squares really well and you're willing to try them out. Second type of problem is this. And in these ones, what you're going to have to do is get rid of the radical in the denominator. My recommendation to you is I would try simplifying it first, and then I'll show you how to get rid of it. So if we want to simplify 24, I'm going to stick with method 1 here. We're going to have root 24, split it up into, let's say, 2 and 12. 2 is prime. 12 will split into 4 and 3. 3 is prime. And this 4 will split into 2 and 2. All right, here we have a pair of 2's. So we're going to have a 2 on the outside. And here left over, we have a 2 and a 3. 2 times 3 is 6. So we're going to have 6 left over underneath. So this is going to be the same thing up here as 3 over 2 times root 6. The way that we get rid of roots when the denominator is we're going to multiply both the top and the bottom of the fraction by the same thing, which basically means we're multiplying by 1, because anything divided by itself is 1. So we're going to multiply the top and the bottom by root 6. Square roots can only multiply with each other. So the root 6 that we're multiplying by will not multiply with the 3 and make 18. It won't multiply with the 2 and make 12. But it will multiply with the root 6 on the bottom to make root 36. The square root of 36, though, is just 6. And that's a good rule to know. Whenever you have a root times itself, it's going to make the number that's under the root. So this is going to turn into 3 root 6 over 2 times 6, which ends up over 12. We can divide the 3 and the 12 because they're not under a root, so they can combine with each other. But we can't do anything with the root 6 because it's underneath a root. It can't be affected by anything else. So this is going to turn into root 6 over 12. We get that by dividing both the 3 and the 12 by 3. The 3 turns into 1, the 12 turns into 4. Last example, this one. And this one's really going to show why simplifying first can sometimes be a very helpful idea. So we start with 50. 50 splits one way into 25 and 2. You could also split into 5 and 10, but I'm doing it this way. So we have a 2. 25 splits into 5 and 5. Those are both prime. And those are also both a pair of numbers. So 5 goes on the outside. We have a 2 left over. So we have 5 root 2, which means this can be rewritten as 5 over 5 root 2. Well, finishing this problem up is really one step left. All we have to do is cancel out the 5s and turn them into 1s. And that gives us 1 over root 2. Of course, there is one extra step, I guess. We need to get rid of the root 2 in the denominator. And again, the way we'll do it is we'll multiply top and the bottom by root 2. Give us root 2 over 2. Remember that when you have a root times itself, you're going to end up with the number that's under the root as that answer. So that is the simplified form of 5 over root 50. These problems can be kind of complicated. You're probably going to need more practice, and you'll get that tomorrow in class. So, hope this video helped you. If not, see you tomorrow, and we'll try clearing things up for you.